linear and nonlinear. What do you think linear means?
Straight.
It's a line, right? Like we've got a line, it's a straight line. Nonlinear would mean not a line. So we've got some sort of curvature to whatever we have going on. So we're going to compare and contrast the two. So we've got two different columns here. We've got stuff that's linear, stuff that's not linear. So linear functions are not raised to a power other than 1. Kind of a hard way to say that. Basically what it means is you're going to have an equation like this. Do you see how there's no exponent with my x? Right? There's no exponent there. What's really hiding there? A 1. And so that's a 1, so it's linear. So anytime you see just an x, that's going to be the graph of a straight line. So what it is, it's a linear graph. I'll give you another example. We could have 5x plus 1. And then what it's not could be something like a parabola. And what it's not would be something where you have an exponent other than 1. So exponents of 1 are linear. Any other exponent? Nope. And even if your variable is your exponent, that's not okay either. So truly the only time it's linear is when this is your variable and there's an exponent of 1. So over here, this would include points that do not lie on a line when you go to connect them. It cannot be written in the form y equals mx plus b. Ooh, do we remember the name of this form? Yes, nice. Alright, so an example of what it could be, again, anything other than being raised to the first power. Now, take a look at this, and do you see how within that I have something raised to the first power? Okay. I do have something, and if I covered up this part, it'd be linear. But because of the x cubed, it's not. So even if it has part of it that looks linear, if it has any part that's raised to any other power, that kind of trumps everything, and it is not linear. So example 1 wants us to look at some equations, and we want to decide if they are linear functions, and we want to justify our answer. Anytime you see the word justify, that means give me a little explanation. No, it's not English class, and you don't have to write me an essay and cite your sources and all the things, but give me a little information anytime it says justify so I know why. Typically on a test or a quiz, these are 2-point problems. 1 point because I'm going to give you a point for telling me if it's linear or not, but then another point for you explaining to me why it's linear. So let's look at the first one. Linear or not?
Yes.
Yes, why?
Because
It doesn't have an exponent, so basically we have a degree equal to 1. So it's linear. Why? My degree is 1. So remember your degree of a polynomial, and we'll talk more about polynomials later. Polynomials are just lots of terms. Okay, so maybe 5x squared plus 3x plus 12. So you have different terms, and those polynomials are linear when your degree, your biggest exponent, is 1. Alright, look at number 2. Linear or not? Not. So I'm going to say non-linear. Why? What's my degree?
2.
Yes, because the degree is 2. So again, any other degree other than 1, anything bigger. How about number 3? What do we think? Linear or not? Linear. Even though it's minus? Are we okay with minuses?
Yeah.
Yeah, we're okay with minuses. So when we see a minus in front of the x, that means it's going to have a negative slope. So it's just sloping downward as we look at the graph. So if I look at number 1, that would have been a positive slope. And then this one just has a negative slope. So that's okay. It's still linear. Why? Because it's still degree 1. So again, notice I'm not even writing a complete sentence there. I'm not a stickler about that. But when I say justify, you do have to give me something. Okay? Ooh, this one's written kinda funny, it's not written in the form y equals. Let's move stuff around, so it's written in the form y equals. Do you see how all of these were set up so nicely for me? Let's set this one up nicely. How can I remove the 3x? And notice the 3x is positive. How can I remove it?
Subtract.
Subtract it, yes. It's a trickier question because the y is negative. So I have negative y equals negative 3x plus 15. So I subtracted the 3x over, so now it's gone from this side, it moved over here, so it's that negative 3x. It's still not quite in y equals form. How can I make it just a y? Divide or multiply by -1, right? It's kind of tomato, tomato. You can do either. I'm gonna think multiply because I feel like multiply always settles in my brain a little bit easier than division. So this will become positive y. A negative times a negative is a positive. A negative times a positive, negative. Okay, so now we're looking at it in the y equals form so we can tell a little bit better what's going on. Now, what do we think? Linear or not?
Linear.
Linear, because is it degree 1?
Yep.
It sure is. So if it's not in your y equals form, you want to switch it over first. Sometimes you might have to divide or do things that end up making it not a linear function. So that's why you want to put it in that correct format first, and then you can for sure tell. Alright, 5 through 8 are just the eyeball test. So flip your paper, and you are just using your eyeballs to tell me, is it a line or is it not a line? Like, literally that easy for these. It doesn't even say justify, so it just says tell me. What do we think about 5? Linear or no?
Linear.
Linear. 6.
Curved.
Yeah, it's curved, so we're gonna say non-linear. How about 7?
Curved.
Curved, so again, non-linear is gonna be our word for that. So don't write curved, make sure you're writing non-linear. Okay, so this one's just straight across, it doesn't have any slope. What do we think? Linear? Linear, it's still a line. What if I had a graph that was vertical? It'd still be linear. So those are kind of special cases where we don't have a normal slope, but they are still linear. Alright, next, intercepts of a graph. Intercepts are when your graphs intersect or touch the axes. So remember that this is always your x-axis, this is always your y-axis. So your x-intercept is where the graph touches the x-axis. Now, anytime your graph touches the x-axis, your y value is always 0. And then, if we think about our other axis, anytime we touch the y-axis, what is our x value? 0. So that's something important to know. So one nice thing about that is we can plug in zeros to figure out where the intercepts live if we need to. Now, these problems are even easier than that. We don't need to plug in, it's just saying, where is it? So we just need to look at the graph. So again, just kind of using our eyeballs here to look at the graph. Is this my x or my y-intercept? X-intercept. So I'm going to label it. You have to tell me which one it is. So it's my x-intercept, and it lives at what ordered pair? How would I write that? 12, 0. Perfect. So remember when you're writing your ordered pairs, and I feel like every year I came back to school after a summer off, I had to remember again, right? So this first thing tells you how far left or right, and then the second number is your up, down. So always left, right, up, down. So always x, comma, y. Alright, let's find our y-intercept. Yeah. 0, and then it's down at -12. Now, you can have graphs that don't have a y-intercept or don't have an x-intercept. You can also have graphs that have multiple intercepts. So there are different situations that can arise. It's not always that you have one of each. What is my x-intercept for number 12? Ooh, we're estimating. Ooh, I like it. -0.75, comma 0. I'm in. So as long as you're somewhere in that same vicinity, if you're like, no, Miss Bessel, that's closer to negative 0.9, that's fine. That is not the hill I die on, okay? So as long as you're kinda in that same general vicinity, again, we are just asking to estimate, I'm not asking you exactly where it is. Alright, what do we think about the y-intercept? Where do we think that one lives?
Negative 1.5.
That's what I was gonna say.
0. I like rounding to the nearest half.
I know, I like rounding to the nearest tenth too. That is usually my go-to. Ooh, 13 is kinda interesting. Why is 13 interesting?
There's no parabola.
Yeah, it's a parabola and it's also what?
It's only one intersection.
Yeah, it's one intercept and it's the same for both. So my x and y intercept are both 0, 0. You guys, I saw the best math shirt the other day. I am definitely into like dorky math jokes and math teacher t-shirts and such. It had a picture of a parabola on it, and parabolas are quadratic equations. So it said working on my quads. I laughed for about 5 minutes, and I also decided I needed it. And then I sent Miss Whipple a text and was like, we need to buy this shirt. And she's like, yup, I'm in.
Did you wear it today?
No, I haven't actually bought it yet, but I need to buy it.
You need to buy
It was like one of those shirts online where it's like, the more you buy, the cheaper it is. So I need to like, I gotta get Mr. Toby in, you know what I mean, or Mr. Cook. Like I gotta go recruit some more people. Anyway, alright, next. X-intercept. Ooh, how many does this have? 2. So we need 2 x-intercepts. Okay. What do we wanna say? What do we think they are?
Maybe 0.5. Then
Careful, look what you're counting by. So you're counting by 2.
all 1.
Yeah,
One
so
and -3.
yeah, I'm gonna go -1 and -3 as well. So -1 comma 0, -3 comma 0. It doesn't matter which order you tell them to me in. And then I only have 1 y-intercept.
3.
Yeah, I'd say that looks like 3. 0 comma 3. Cut up a little bit. So again, we're just estimating. We're not even plugging into an equation. We're gonna be given the graphs and we're gonna say, ooh, it looks like it's here. Flip when you're ready. We're gonna talk about what the x and y intercept mean when they are real life situations. So now we've got a table. So we have Juan, and Juan got a gift card for his birthday. And he's gonna use his gift card to pay for a video game subscription. And it shows the funds remaining. So initially he got $50. And so we can tell that his subscription it's weekly. Each week is gonna be $10. So he's paying $10 each week. So let's start with the x-intercept. The x-intercept is when what is 0? Y. So remember, this is x, this is y. So the time is my dependent variable. The time doesn't depend on anything. The amount of money I have left though, well that depends on the time. So this is independent, sorry, I might have said that backwards. X is independent, y is dependent. So x comma y. I did that the other day too. Okay, so my x-intercept is when y equals 0. It says, what is the x-intercept? So x-intercept, y equals 0. What does this mean, this line? What is that telling me? I have what? How much money I have. So how much do I have left?
0.
Nothing. So on week 5, that's when my gift card ran out. So when I have no funds left. So what does the x-intercept tell me? When I have no funds left, because my y value is 0. So let's think about that same question, except for the y-intercept. The y-intercept is when what is 0? What's 0? Not y, but x. Okay, so it'll be this top one. What does this represent, this first thing?
No time spent.
No time has gone by, right? So how much money do I have initially? So this would be how much money do I have to start? And again, you can write that in different ways. You're gonna write it in your own words, a way that it makes sense to you. But you need to, like I said, explain to me what those are. So what are the x and y intercepts? Oh, I did this part. I did what they represent. This one wants me to tell just what is it. So let's tell what it is. The x-intercept itself is what? What number? What value? 5, 0. And the y-intercept is 0, 50. Okay, so I answered kind of the question of what it represents first, and then I went back and said, okay, but these are the values where they live. Okay. We are launching a rocket on our next problem. Do you see how at time 0 is at a height of 24 feet? So that means it's sitting on something that's 24 feet. So I have my rocket, it's 24 feet in the air, I launch it, it comes back down. That would make a parabola too, yes?
Yeah.
Okay, that'd be another quadratic equation, that'd be another parabola. Okay, so what are the x and y intercepts? So this one just wants the facts. So x-intercept is when y equals 0. So what is my x-intercept in terms of numbers? Using the table, what's my x-intercept? 6, 0. Perfect. What is my y-intercept just in terms of the numbers? 0, 24. Perfect. Then, this is where we get into the what do they represent. So let's start with the x-intercept. So the x-intercept is when we have 0 for y. So think about your rocket. If it is 0 feet up in the air, what has happened? It is now on the ground, right? So the x-intercept is when the rocket hits the ground, or it lands, however you want to say that. The rocket hits the ground. Again, I'm not going to be picky on how you word it. If you said when it lands, that's the same thing to me. Alright, so now let's go to y-intercept. The y-intercept was when we had x equal to 0. So 0, 24. What did that tell us?
It started to.
Yeah, it gave us our initial height. So our initial height. Or you could say the height at the time we started. There are different ways to say it. Again, I'm not going to be super picky about that as long as what you said kind of makes sense and means the same thing. Are we okay with intercepts? Okay, we're going to move on to our last topic. And this one tends to be a little bit trickier. It's almost one of those like mind game word problems where you've got to think which category things fit into. We're going to start by talking about line symmetry. So line symmetry is when you have a graph and it can be reflected over, so it can be reflected, and this should have said this, so switch that to over. It can be reflected over a vertical line so that the graph looks the same on both sides. So let me show you an example of a graph that has symmetry. Well, that marker is useless. So again, I'm gonna work on my quads again. I'm gonna put up another, so if I have a graph like this, do you see how it has line symmetry? That there's a line that cuts it in half. Now the line doesn't have to be an axis. Sometimes it is, but not always. So if you have a line that cuts your graph directly in half where both sides look the same, then it has line symmetry. So that's what that looks like. So again, thinking about reflections. Point symmetry is another type of symmetry, and that's when you have rotational symmetry. So you have something that is rotated about a point. And I'll show you what that looks like. So take a peek down just a little further. I basically just drew the same graph over here, right? You see how I have line symmetry going right through the middle? Line symmetry cuts it right in half. This one, so this is line. What type of symmetry? Line. This one is a point symmetric graph, and I'll show you why. And you kind of have to use your imagination a little bit because we've got a two-dimensional graph that obviously I can't pick up and move or do anything to, right? So put on your imagination hat with me. My point symmetry is at the origin for this problem in particular. This is where the point symmetry is. So if you can take part of the graph and think about rotating it, would it land back on top of itself?
Yeah.
Okay? So again, you kind of have to use your imagination a little bit, but that's what point symmetry is. Okay? Look, we got one more page. We're almost there, people. This is where I usually tell my Easton Bessel story, and I don't know that I can tell as many stories about him because now he's at the high school, and so I feel like, but this is still a good one. This is from preschool, so I feel like it's fair game, right? He was 4. I feel like I can still tell this story. It wasn't even bad. So he came home from preschool, and I was like, hey buddy, what'd you learn? He went to Rainbow and Openness, right? Like, I love how preschools have those nice, like, happy names. So he comes home, and I'm like, what'd you learn, dude? And he's like, I learned about cemeteries. And I was like, whoa, that's dark for Rainbow preschool. Like, and so my husband, who's more chill than I am, is like, tell me more about that, buddy. What'd you learn about cemeteries? And he's like, I learned that it's when things look the same on both sides. And we were like, oh, you learned about cemeteries. But he came home and said cemeteries, and I was very concerned about what was in our curriculum for preschool for a moment there, but it was okay. Turned out to be okay. All right, now, within these symmetries, we can be even more specific, and we can say that graphs are even or odd. Now, a graph that is even has line symmetry, and the line symmetry is specifically the y-axis. So if you have line symmetry specifically at the y-axis, then that's going to be what we call an even function. You can have line symmetry in other spots, and it wouldn't be even. So let me show you what that would look like. So let's say I have a graph, and we'll still go parabola. Working on my quads all day. So I still have a parabola. Is the line symmetry for this the y-axis? No. No. So this is something that has line symmetry, but is not even. So that can happen. And that's, like I said, where we kind of play these mind games and it gets a little trickier. So you can have something with line symmetry that is not even. So even things have that extra piece of information that not only must they be line symmetric, but that line of symmetry has to be the y-axis. Now, here's something interesting when that happens. When that happens, our f of x value and our f of negative x value are the same. Let me show you what I mean by that. That's an important statement. All right, we've got these 2 points. I'm going to pretend this point is at 2, 0, and I'm going to pretend this point is at negative 2, 0. Remember that in function notation, if I am finding f of x, so let's say I'm finding f of 2, f at 2 would be equal to 0. So if you're finding f at x, if I plug in this x, it would be equal to 0. If I find f at negative x, what's that equal to? So the negative version. What's this one at? Also 0. So do you see how these 2 things were the same? If these 2 things are the same, and these signs switch, then we know that it's even. So it's kind of a little like litmus test that you can do to check and see if these are even. All right, now we have odd functions. Odd functions are rotational or have rotational symmetry, but specifically they have to have it to the origin. So kind of like the last one, we're just going to be extra picky. So odd functions have rotational symmetry, but it must be to the origin. So let's kind of put something on the other side again like we did a minute ago. Let's say we have the same graph. So this is kind of what a cubic function looks like, by the way, or another odd powered function. This one has point symmetry, but it is not odd because it doesn't have point symmetry to the origin. So this one has point symmetry, but not to the origin. So it is not odd. So you're going to get choices eventually, and they're going to say to you, is it even, odd, or neither? Even, odd, neither, neither. Okay, so there are three choices. Again, there's no mysterious choice hiding behind door number 4. It's 3 choices total. Okay, so it's even, odd, or neither. So again, even, odd, neither for both of those. Another thing to notice, and let's make up some points here. Let's say we have a point at -1, -3. And then let's say this point lives at about +1, +3. In order to be able to tell that it's an odd function, if you find f of x, so remember this is my x, so if I find f of x, I would get 3. If I find f of the other x, I would get -3. So look at this statement right here. It says if you look at the positive and negative, they should be the opposite of each other. Are those the opposite? Yeah. So that's another way to look for it. So if you don't have the graph, but you know a couple points, you can still tell if it's odd or even. Alright, last example, are we ready? It says, determine whether the function is odd, even, or neither. Ooh, and we have to confirm it algebraically. Okay, that is some work we have to do. Okay, that's fine. We got this. What do you think about 19? Odd, even, or neither? Even. It looks even. So we think it's even. We're making a hypothesis, right? We'll use a fancy science term there. We're making a hypothesis that it's even, but we gotta check. So let's check. So when I go through to check, I'm gonna find a point on either side. So this point would be 1, 8. This point would be -1, 8. And it says to show me that it's true. So f of 1 equals 8. F of -1 also equals 8. So this matches to this rule. So that's how we can tell. Now, on this one I'm going to pretend that I don't see the graph. Let's try this one without thinking about the graph for a minute. Let's plug in 2 numbers. So I'm going to plug in, we'll plug in 2, and we'll plug in -2. Now, if it's even, I should get the same thing, right? Both 5s, or both 7s, or both -12s. If it's odd, I should get +7 and -7, or 9 and -9. Does that make sense? And if it's neither, they won't have any relationship. I'll get like 3 and then 1/2. No relationship, okay? So let's plug it in and figure out what we're gonna get. And you can type these into your calculators. By the way, this is a good time to introduce you to my calculator. This is Pinky. Pinky the calculator, so if you ever hear me and I'm like, Pinky, where are you? I'm looking for my calculator. Alright. I want to be careful how we type this in, so that's why I want to show you. You can type it into these calculators as well, you're gonna type it in the exact same way. So whether you have scientific or graphing, it doesn't matter, you're gonna type it in the same way. So let's practice together. I see a negative sign. So for the negative sign, on your calculator you should have a negative. Don't use the minus, we truly want this little negative thing right here. Then, anytime you have something being raised to a power, that something should live in what I call a parenthesis house. So I'm going to plug in 2 in place of x, but I'm going to plug it in a parenthesis house. So do you see how I'm plugging it in place of the x? So I've got my negative, I've got my 2, and then I need to cube it. I call this the caret key. So I'm going to hit to the 3rd power. So that is my caret key that raises it to the 3rd power. And then I need a minus. Now, do you see how if I have a graphing calculator like I'm up here in the stratosphere? If you have a graphing calculator too, you're going to need to arrow right to get it to come back down. Then I'm going to put minus. And then I've got a 5, and I'm plugging in 2 again. So you'll notice whenever I plug in numbers, I plug them in what I call a parenthesis house. And I'm sure there's a better way to say that where I don't sound like a kindergarten teacher, but I don't know what that way is. So again, I took the 2, and I plugged it in a parenthesis house. What do you get? Did you also get negative 18? Yes? Alright. So, if this one's negative 18, then it's even. If this one's positive 18, then it's odd. If it's anything else, it's neither. Does that make sense? Okay, so let's see what we get. We're going to do the same thing. We've got a negative, but this time we're going to plug in a negative 2 in the parenthesis house. Yes, you have to use a parenthesis house when you plug in. And yes, there's a better way to say it. I'll figure that out later. Maybe that's what I figure out in year 22 of teaching. Alright, so I put my negative sign, and then I need another negative sign inside, and then I need to raise it to the 3rd power. I'm going to arrow right to get it to come back down. If you have a scientific calculator, you don't need to arrow right. Minus 5, another parenthesis, negative 2. I got 18. What does that tell me? It's it's odd. So when they have opposite signs, it's odd.
Oh, I remember this one down as small.
Yeah. Opposite signs for like what the result is going to give me an odd situation. If it had been negative 18, it would have been even. If it had been 6, it would have been neither. So those are kind of all the options that are out there in the world. I'm going to triple check the homework and make sure that I like all the problems, because sometimes year to year I'm like, oh, I don't like this one as much. But I'm planning on page 19 to 21 for homework, and you've got time right now so you can get started. So this is assignment number 2. So you, oh no, 3, right? That should be 3, because we did assignment 1 was bookwork, assignment 2 was the worksheet. Okay, so this is assignment 3, page 19 to 20. You're going to do numbers 2 through 24, the evens. So you will do 2, 4, 6, 8. Should you do number 7?